Hi, can everyone hear me? Everything good? Okay, thanks. So, welcome everyone to this workshop, part of DSS. I really appreciate you being here because there are so many competing talks, each one more interesting than the other, so I really appreciate you being here. I am Vesselin Velichkov, ZK security researcher at OpenZeppelin. I'm part of the ZK team, and what we do audits of ZK cryptography components, and also we try to educate our auditors about cryptography and ZK in general. And what you are going to hear today is part of this training process. So I'll be talking about MPC computation for coSNARKs. So I just want to check a bit, like to get a feel of the audience, like how many of you are vaguely familiar with SNARKs, ZK SNARKs, ZK STARKs, like vaguely familiar? Okay, cool. And how many of you are deeply familiar, like to the technical details, like how Plonk works, how Grot16 works, commitments, polynomials, polynomial arithmetic? Not many. Okay, you're at the right place. And have you heard about coSNARKs? Yes, cool. So yeah, so this talk is about SNARKs and coSNARKs. The idea is to start from the ground, so hopefully we will introduce everything that's not familiar to you. But the goal is to illustrate multi-party computation of coSNARK, so how you collaboratively compute a SNARK proof. And the motivation of the whole talk is that like many people, especially like many auditors, are interested how coSNARKs work. And if you want to explain this, you need first to start with explaining how SNARKs work. And then SNARKs is already a deep area in itself. Like if you start with some production level SNARKs like Plonk or Grot16, there are so many new concepts that you need to introduce before even touching the area of MPC that it's simply not feasible. Like it makes up for a whole new course. So that's the reason why we take a different approach. We start with a very simple protocol called Sumcheck. It's an existing protocol, it's an old protocol, it's widely used today, even in production level SNARKs and STARKs. So we start with it, and then directly we jump into MPC. So with Sumcheck, we illustrate what it means to prove something, in particular what it means to prove correctness of a computation, and then we directly discuss multi-party computation, how you can collaboratively compute this proof. And once we are there, then we can introduce all the topics that are related to ZK SNARKs, such as, for example, succinctness, commitments, blinding, arithmetization, and this will not be part of this talk. So this will be, I will mention it only at the end, and the idea is that the toy protocol that we develop is modular enough that you can build on it, and once you're comfortable with MPC, you can also start introducing all those critical components. Okay, so that's briefly the plan I will follow. So basically the whole workshop is broadly divided into two critical parts. So one is introducing Sumcheck. So how many of you are familiar with Sumcheck? Oh, cool. That's nice. And if you are not, we'll spend quite a deal of time like introducing it, maybe about 20 minutes or so. And after that, we will show its MPC version. So how you can collaboratively compute an MPC proof. And at the end, depending on how much time we have, we will talk a bit about the missing parts, what we still need in order to build a full-fledged ZK SNARK. Okay, just to clear up some basics in the beginning, what is zero-knowledge proof of knowledge? So basically, it's a protocol between a prover and a verifier, in which the verifier proves the prover proves that they know a certain fact, which we call the witness, for some public statement and a public input such that given relation holds. Now it's a mouthful. We have this y equals f of x comma w. So you can think of w as the secret input, the witness. X is the public input known to prover and verifier. You can think of f as the relation and y as the public statement. And just to relate it to something familiar, a simple example is proving knowledge of the preimage of a hash function. So you as a prover want to prove to the verifier that you know such a W, like a pre-image to your hash function H, that when you hash it, it results to the output Y. So W would be your witness, it's secret, it shouldn't be revealed to the prover, to the verifier, sorry, and Y is your public statement, H is your relation or the hash function. Okay, and in the protocol we have some interactive process between prover and verifier, and it can also be made interactive, non-interactive. ZK SNARKs are one class of ZK proofs of knowledge. Just a few words about them. Just to break down the whole like acronym, zero knowledge, succinct, non-interactive argument of knowledge. Zero knowledge, the proof does not reveal anything besides its validity. Succinctness means the proof is short. We will talk a bit more about what short means, but basically it should be short in comparison to the size of the witness and to the computation. Non-interactive means that you don't have like a sequence of messages between prover and verifier. You only have a single computation on the prover side, then submitting the proof to the verifier and the verifier verifying it, and finally argument of knowledge. So the prover proves not only that that there exists a witness that satisfies the relation, but also that he knows this witness. And finally, just a note about difference between proof and argument. So we will be using the two interchangeably in this talk, but technically there is a difference, namely a proof is about proving unconditional soundness, or unconditional security, meaning security for unbounded provers. So we don't assume that the prover is computationally limited. While argument is more about all our proofs will be under the assumption that the prover is computationally bounded, namely he is polynomial, he can run at most at polynomial time. Meaning that if you have a more powerful prover, he can also break the system, he can fake proofs. This is just a technical detail. And the core properties of ZK SNARK, completeness. So an honest prover will always convince a verifier, probability 1. And soundness is about the fact that you still have some probability, some possibility to cheat. So there is still a possibility that a cheating prover may convince a verifier that he possesses a witness, even if he doesn't. But typically this probability is negligible, so it's not feasible to find such a witness. And finally, zero knowledge, we talked about it, doesn't leak information about the witness. And two properties that are desirable, but most commonly they are present: succinctness, so size of proof, and the proving time is sublinear or even nearly constant in computation size. And non-interactivity, we discussed it already. So specifically, ZK proofs have found wide applications in blockchain, and they actually were a catalyzer to quite a bit evolve the field, even research-wise. In particular, they are very useful for scaling and privacy. So scaling, it's ZK proofs that allow, for example, ZK layer 2 rollups to batch multiple transactions together off-chain, produce a single succinct proof proving that these transactions are valid, and they cause a valid transition from a route to the next route, and then only post this succinct proof on-chain, which is critical because that's what we are paying for. So we pay for the size of the proof in gas on layer 1. And thanks to ZK proofs, then it becomes cheaper and therefore scalable for Ethereum. And for privacy, which is a big buzzword in this edition of DevConnect, it's clear how it helps privacy, right? Because of the zero knowledge property, you can hide identities and amounts while still making it compliant, still being able to prove that a transaction happened, for example. So this is how it looks. It's like a high-level workflow. On the left-hand side, you have off-chain computation. So a program or a circuit. This may be like a circuit of your VM. A public input and a witness, then a prover or sequence that computes a proof. This is completely off-chain. He passes the proof together with the public input. So you have the public input and the proof to the verifier, which is typically a smart contract on-chain, which checks whether the proof holds or not. And now, slowly moving to the core of this topic, like coSNARKs. What are they are? What they are? So the thing is that like everyone is focusing on the verifier. So we've gone through long lengths of making sure the verifier is efficient, because you want your cost to be low. But the reality is that the prover is the bottleneck now, because proving is expensive in terms of time and memory, but it is also like not so critical because it happens off chain. Yet, if we want to like onboard resource constrained devices, like for example mobile phones, if we want our mobile phones to be able to compute ZK proofs, it would be nice if we can outsource the computation of a ZK proof, for example, to the cloud, where it has much more powerful servers and they're able to do this. On the other hand, we also want to keep the witness secret, right? We have secret data. So how do you resolve this? How do you, on one hand, outsource your computation, and on the other, you still keep your data private? And that's the whole motivation for proposing coSNARKs in 2021 by Özdemir Bone, in which they propose to outsource this computation to a network of MPC servers. And MPC stands for Secure Multi-Party Computation, which is exactly the technique that allows us to securely share the witness, so share the secret input to our proof, to a network of nodes in such a way that none of them learn anything about the witness itself, yet they can perform some meaningful computation on their part of the witness, and then accumulate their results together and come up with the final proof. And that's the whole process we will be talking in more detail now. And the same picture as you saw before, except in the MPC setting. So all the components are more or less the same, except now we have this network of provers. So these are MPC nodes, which receive as input, instead of the witness, you notice here they receive this special notation like square bracket W, with which we denote shares of the witness. So now every node will receive its small piece of the witness. We will see how these pieces are computed, and they will perform computation on those pieces. They will come up like conceptually, each of them will produce a small fragment of the final proof, and then combining all the fragments, you end up with the full proof, which is then pushed to the verifier. And if you notice, from the point of view of the verifier, things are the same. So the verifier cannot tell whether whether the proof came from this MPC network or whether it came from a single verifier. And there are already production systems that implement this approach. Tasio is just one example where you can see like the end users in the form of mobile phones, for example, that they push their computation to MPC nodes. So hopefully by the end of this workshop, you will have a at least better feeling and intuition, but hopefully better understanding of what is happening in all those MPC nodes and how all this process works. It's not to say that it's exactly what Tasio does, but it's more like conceptually understanding it. So this here is a whole roadmap of how you would go to build up a simple toy ZK SNARK from the ground up, basically, such that it is MPC friendly. And we start with the Sumcheck protocol, which we introduce in a moment. Then we add MPC computation, and then we add all the other components that are needed for a SNARK, like blinding, commitment, succinctness, and arithmetization. But in this workshop, we focus only on those two first blocks, simply because time is limited. We will talk about proof of correctness and then outsourcing this proof of correctness. Okay, are we good so far? So any questions? Okay, I'm not sure how you can ask a question in this setup, but maybe if you raise a hand, I'll come over and ask you. Okay. Okay, so Sumcheck. I think we can easily spend about, let's say, probably about 20 minutes just talking about Sumcheck, because that's the underlying part of the whole, of everything that follows. So the Sumcheck protocol basically comes down to proving knowledge, and it's a bit of a weird setting when you state it at first, but later on we'll see how it can be useful. So you have a function, and you want to sum this function over all of its inputs in the Boolean hypercube. So what Boolean hypercube means is just all the 0, 1 possibilities of the whole n-bit string. So you have n variables. They are not necessarily defined in F2, not necessarily Boolean. They can take any value in the field, but you evaluate them on 0 and 1. And you take like 0, 0, 0, 1 plus 0, 0, 1, 0 plus 0, 0, 1, 1, and so on, 2 to the n. And you compute your value t prime. And the whole protocol is about proving to a verifier that this function sums to a particular value t prime. Why would you want to do this? It's about saving computation. So in this setting, we are completely clear. Nothing is hidden. Both the prover and the verifier know the function f. They know their degree. Sorry, it's a polynomial. The polynomial f, they know its degree. But computing t prime is computationally expensive. Like n, if n is, for example, of the order of 32 or more, then you need 2 to the 32 operations to compute this t prime, and the verifier wants to save this. He doesn't want to do this. So the prover says, okay, I have computed this t prime for you, and this is the proof that this is correct. So then the verifier engages in this Sumcheck protocol and verifies that, okay, indeed that's the correct result. So then his computation goes down from exponential 2 to the n to actually linear in the number of variables, which is a huge saving. And of course, looking at this at the moment, it's a bit like, it's very strange how it would even relate, you know, to ZK proofs, because in ZK proofs we talk about an arbitrary computation. But it turns out that this very simple protocol, just working over the booleans, you can, with some additional, you know, techniques, you can easily turn it to be a proof of correctness and later of knowledge for an arbitrary computation. Yes? Sorry?
Can you clarify exactly what's being summed?
What is... Yes, so the question is what exactly is being summed here. So let's say this f is some polynomial, maybe like x1 squared plus x2 plus 3. And then you take x1 and x2, you make them 0, 0. And this gives you some value. Then you give 0, 1, you add it. 1, 0, so it's like an accumulator. Yes? Oh, so the question is if the inputs are not Boolean, how to make them Boolean. In fact, they are not Boolean. So this polynomial will be, we'll see later, this polynomial will be defined over a field. So these values can be any element of the field. But for the protocol, you only take the 0, 1 values. Because it's a polynomial, you can take literally any value in the field, and 0 and 1 are as valid as anything else. And we'll see how it translates later on to SNARKs. More questions? Yeah, so this is the setup in a bit more details. So we have the function, we define it in this way. We have the n variables as before, and now think of this w1 to wk just as constants that parameterize this function. But we need them here because later on, when we want to add zero knowledge, we want to speak about a witness, we want to speak about secret part. And then that's when this will come handy. So this will be potentially our secret that we want to preserve. But for the moment, these are just constants. And the polynomial is defined over the field f. It's like a field of prime order, doesn't matter. And also an important detail is that the degree of the polynomial is bound. So every variable will show up with degree not more than this. So you will have x1 to the d minus 1, x2 to the d, but you cannot have xi to the d plus 7 or whatever. So you're bound by degree. And that's important for the soundness. We need this D to be fixed and relatively low compared to the size of the field when later on we want to prove soundness of the protocol. And the first step is the prover computes this huge sum. That's his computational bottleneck. He comes up with the value T, and then then it engages in a protocol in a certain number of rounds. The number of rounds is the number equal to the number of variables, and every round is like conceptually the same thing is going on. So once you accept the last round, it's a bit special. So as long as, like, when you understand one of the rounds, you have understood the whole protocol, basically. So in every round, the prover will be sending always a polynomial of a single variable, and this variable will be progressively one of the variables of the F polynomial, like first one, then two, and so on. So in round one, prover sends P1 of X1, and how does he compute this polynomial? Well, he takes the original polynomial F, he leaves X1 to be free, so the polynomial will be in X1, and then he sums all the remaining n minus 1 variables. So he assigns them. So here we have a sum over 2 to the n minus 1. And this just remain fixed as before. So in a sense, you get something like this T prime, but it's another constant. Then the verifier, upon receiving this polynomial P1, he first checks the degree, because the whole polynomial is bound by D, so this P1 of X1 must be also of degree at most D. And then the verifier performs this simple check. Now, he takes this P1, he evaluates it at 0, then he evaluates it at 1, he adds the 2, and here it's obvious that the sum of the two should equal T prime, right? So that's the first check that he does. Of course, T prime may be, like the prover may be cheating, that might not be the correct value, but this, if he is cheating, we will recover this later on, specifically at the final round. Okay, so if the check passes, the verifier samples a random number. So that's where the whole soundness of the protocol rests. This R1 or this Ri, it should be chosen uniformly at random from the field. Okay, and this is the interactive version. So just opening a bracket, because I didn't introduce specifically like how do you construct non-interactive versions from interactive, but if you want to make it non-interactive, instead of asking the verifier to randomly choose R1, you may just hash all the elements that were seen before that and get the hash as like this pseudo-random value R1. It's just a detail just to keep in mind that this protocol can easily be made non-interactive as well. But explaining the interactive version, it's a bit better for a start. Okay, and then number I, so you have the same structure going on n times. So at number I, we have the same thing, Pi of xi, this one is free. We're summing over the remaining n minus I values, but crucially, everything that we have processed already is fixed to the random values that were sent by the verifier to this point. And we'll see why this matters. Like basically, when you show soundness, it rests exactly on these random values. Again, the verifier checks the degree, then checks this summation. So the summation here is a bit different in the sense we don't check against the initial value, obviously, but what we check against is evaluate Pi at 0, evaluate Pi at 1, sum them, and we expect the sum to be equal to the previous polynomial that the verifier received, evaluated at Ri minus 1, the previous random value. And if you think about it, that should hold if the prover is honest, right? So the previous polynomial had this one free here, all the summation was here, and the rest was fixed. So by doing Pi 0, Pi 1, you essentially assign 0 and 1 here, and this one was free before, but now you fix it to R minus 1, which is exactly what how this Pi is defined. So for an honest prover, this equality should hold. So I'll give you a chance for questions in a moment, but just want to complete the description. This is the final check, and in the final check, we have already assigned all the values to this random variable, so all the variables to these random values. So at this point, the verifier actually evaluates the original function f, so the real function. At this point, you cannot give him a fake function because he knows it. He will evaluate it at R1 to Rn, and he will ask whether this evaluation equals to the last sent polynomial, Pn of R of n. Now, this is the check that binds the final sum to the original polynomial. And if you remember, the first round was the check that bound the claimed value to the first polynomial. Now, if you think about this, what happens is like you have a inductive binding. You bind the last polynomial to the previous to the next one, and so on, and so on, and so on, until you reach the top value, which, like, if all checks pass, then you're sure that the sum is correct. I mean, it's more than this, but like algorithmically what happens. Okay, any questions? Did I manage to lose you already? I already see faces looking at their phones. In the beginning they were more fresh. Now I'm starting slowly to lose you. No, but ask anything if you want to. I have a very nice animation right now, which hopefully will make it a bit clear. Okay, so take this very simple example. We have a polynomial in 3 variables, x1, x2, x3, and we want to apply some check on it, which means like evaluating on the hypercube of dimension 3, which is just the cube in 3D. And the blue dots are simply the points at which we want to evaluate our polynomial. So we want to sum basically all the blue dots. And how we go about it? What happens, like, conceptually when we do the P1 x1 polynomial is we are dividing all the values like in 2 sets. One is the blue dots, the other is the red dots. So the blue dots you get if your x1 is 0, so we are here, and then you work only on this face of the cube, and the red dots happen if x1 is 1, so you work on this face of the cube. So essentially the first check is nothing but like summing these points and then summing these points, which like obviously is the whole thing, like all of the points. But then the interesting part is that you collapse your dimension by 1. So from 8 points you collapse it down to 4. And how do you do it? It's precisely by fixing your polynomial P1 to some random value, R1, which means, like, again, like hypothetically, that you had this cube, but you also have a polynomial that it can go not only through the values 0 and 1, but just to any field element. And you exploit this to say, okay, I've received this polynomial P1, and now I want to kind of commit to it, I want to fix it, and that's why I just take a random slice of the cube at some random value that the prover cannot predict, it cannot manipulate, and he says, okay, from now on, work now on this polynomial only in this space, which means that now we are back recursively, we are at where we started from, except we have lowered our dimension. Now we need just to sum 4 points instead of 8. And it goes on like this. We divide by 2, summing the blue dots and the red dots. So that now the check is again against the R1 value. Sorry. Then we are at the dimension 1 until we reach a single point, and that's where the final check happens. Now, I guess this is more or less true, but probably what is like hanging in your mind is like, why would it work, right? Like maybe you feel a bit cheated. Like why would this work? And the trick is in those random values, and that's where this Schwarz-Zippel lemma comes into place, which is widely used in many SNARKs actually, and it basically rests on the simple fact that, like, if you have some non-zero polynomial f that is of bounded degree, so some fixed d, then this polynomial can have at most d zeros. So it can be 0 at most d places, right? Now, if you query the polynomial at some random point, just anywhere on the blue line, and this blue line, it can go forever, you know, although we're in a finite field, so it's finite. Now, the chance that if you query the polynomial with this random value r, the chance that it is 0, it's precisely d, the degree over the size of the field. Why? Because it's just the chance that you hit one of his roots. You just pick something at random, and if it happens to be a root, it will be 0. But if it's non-zero, then it means that the polynomial is non-zero. So essentially, this gives you a way to check that a polynomial is really non-zero with just a single random query. So that's the whole magic of it. And if your field is of huge size, like 2 to the 128, and if your degree is even like 2 to the 33, you still are left with a very low probability of like hitting one of the roots. So was this clear so far? Any questions? Because the next slide is actually the connection to Sumcheck. So how does this apply to Sumcheck? Well, the Schwarz-Zippel lemma, what I described is how you apply it to show that the polynomial is non-zero, right? But you can easily translate this to actually checking whether two polynomials are equal. Because suppose you want to check whether the polynomial f is equal to polynomial g, and you know that both of them are bounded by degree d. Well, you can simply say, in fact of checking f and g, I will check a new polynomial h, which is equal to f minus g. And now, checking whether f equals g comes down to checking whether h is 0 or not, and which is precisely applying the Schwarz-Zippel lemma. So then by simply querying h at a random point, if the query turns out to be non-zero, then you know that f cannot be equal to g. But if the query turns out to be 0, then you know with very high probability that the two polynomials are the same. And that's exactly what happens in this critical check at every round of Sumcheck. Like conceptually, we are abusing notation here a bit, but if this is your polynomial from the previous round, and this is your evaluation for the current round, this will be your f, like your f, and this here will be your g. So by this check, you are simply verifying this equality. So by Schwarz-Zippel at every round, we make sure that like the polynomials are correctly chained to each other. And that's where the whole soundness rests on. Okay, we have another 25 minutes. Any questions so far? Yes?
What's the strategy to choose randomness?
So what is the strategy to choose randomness? It should be uniformly random, but you are asking how do you choose it?
Yeah.
Okay, yeah. Well, to make the theory work, it should be like as close as possible to uniform distribution, right? But how do you do it in practice? For the non-interactive version, you just hash the transcript. Your hash is the R. But in interactive setting, I don't know, you flip a coin. What it turns out like, no, seriously, they are called like coin flipping protocols. You know? Yeah. Any questions? Okay, so. Okay, a few words about the complexity, and then we move to MPC. Okay, completeness is clear. I think if the prover is honest, then all the equations, all the checks should work. The prover is not honest, we come down to the probability with which the Schwarz-Zippel lemma does not hold, like the probability with which you may hit one of the roots, which is like 1 minus, so we set it's d over f, but we have n rounds, and now if you do the math by union bound, you end up with n times d over f, but this is still negligible. For communication, the prover sends n d elements because you have n rounds, and at every round you send a polynomial of degree d, so that's like d plus 1 coefficients, while the verifier, he just sends random numbers, so he has complexity order n. The prover is order 2 to the n, and the verifier order n, and the proof size is n d elements. So the proof is not succinct because, as you can see, it's like it grows linearly with the degree. So the longer your polynomial, the longer your proof. And we'll see how we can address this later. Okay, now we go to multi-party computation. So what we have done so far is the ability to prove something. So it's not a proof of knowledge, it's not even a ZK proof of knowledge, but it's proof of correctness. So someone did some computation and he wants to convince you that the computation is correct. You know the function, but you cannot compute it yourself. So all this block here does this proof of correctness. And now we want to outsource this proof of correctness to a network of MPC nodes. So just take as a simple example this polynomial AWX1x2 plus BWX2. Now A and B can be thought of as the coefficients of the polynomial, and then W is your like potentially witness, but it's a constant for the moment, and you want to compute the sum of this polynomial. So like coming back to the beginning, what I mentioned, now the challenge is how do we hide. So the prover doesn't want the nodes to know the witness for sure, but potentially maybe also the coefficients of the polynomial. Maybe he also wants to hide the polynomial. So our challenge now is how to outsource the computation of this sum 2 to the n, like 2 to the 2 in this simple example, without revealing A, W, and B to the MPC nodes. And a very natural way to split a secret value among, let's say, M parties is just to like randomly pick M minus 1 random numbers from the field, like uniformly random, and then the final value, the mth value, you compute it by simply subtracting the sum of everything else, of all the random values that you computed, subtracting it from the original secret value. So the whole goal of this is that you end up with M shares such that when you sum them, you have your secret element W. So here, like you have the secret, you split it into, like in this case, 3 elements, and you get your value. And this, it's super. Yes. Yeah.
What exactly is happening with that W?
So
W is just it's just a field element, yeah?
yes, so the question is what we are sampling here. Yes, exactly. So this W, so first this W without the superscript is just a field element, yeah. And this W with the superscript is also just a field element, yes.
How are you determining what that is?
How
are you determining what W with the superscript is? It's random?
It is random, yes. I'm sorry that I didn't clear up some notation, but like when you have this sign, it means like just draw a random element from the field.
And when you say draw, you just mean basically like pick a random number that's less than the field, subtract it.
Yeah, subtract it from this one. You mean?
Okay. You're just trying to make a set of field elements that sum to the 1.
Yes, that sum to the W. Yeah, exactly. And indeed, so this superscript, like from now on, you will keep seeing it. It just denotes a share, a random share of the value W. And then we have this square W. It means basically the whole vector of shares. It just means that this W is secret shared among M parties. So when you see the square brackets, you think of it like a whole vector of shares. And this method is very simple, very natural, and it already gives like what we need essentially. It gives you perfect secrecy because no less than M parties, so no less than all of the parties can reconstruct the secret value, and they cannot even infer information about it. You need all the M shares in order to get your value, like you need to sum everything in order to get the original W. So that's why it's called M of M threshold scheme, because you need everything basically to reconstruct, and it's very powerful. But you also have T of M threshold schemes where you may need some small fraction of the whole set to reconstruct, for example, like Shamir secret sharing, which is based on polynomials, but it's maybe a bit more complicated to introduce. But this already works for us. And it also has some very good properties, like almost all of the properties are good. For example, it is linear with respect to addition, meaning that if you want to compute the shares of the sum, it's sufficient to compute the sum of the shares, basically. So you have your shares, you just sum the share, and you already have a share of the sum value. And similarly for multiplication by a constant, like you've shared this value x, but you want now to compute the shares of alpha x, and alpha is a public constant. Well, you just multiply alpha by all of the shares in your vector. However, multiplication is the problem, and it's not so simple with multiplication, where you, when you simply multiply two shares, it does not result in a valid share of the multiplied value. And all of this here, it like slowly drives us to the problem of, remember, at the end of the day, we want every node to be able to compute our function, but working only on his shares. So he only knows his own share. He has no concept of the secret values. And that's why these properties are super important, because this simply means that in your function, whenever you have an addition or a multiplication by a public constant, then the node can just do his computation in isolation. He just works on his own shares, and he already provides a valid share. But whenever you have a multiplication, then you are a bit stuck. And that's where you need to do some auxiliary communication with other nodes to get some more information to move forward with the multiplication. And we'll see in a moment how this works. So this auxiliary information comes in the form of these special triples called beaver triples. And a beaver triple is just these three field elements, of which the first two are completely random, like chosen uniformly at random from the field, R and S, and the third one is simply their multiplication. And every party, every MPC node will get a share of this beaver triple for every multiplication in your polynomial. And we denote, like in this way, we denote that the beaver triple is shared. So with the use of beaver triples, how do you compute a multiplication? So that's another, I think, critical part of this workshop. And if you get this, I think we are already on the way to actually compute the full sum check in MPC. So we have the shares of x and y, and we want to compute the shares of z such that x times y equals z, but also remember that none of the nodes actually know x and y. So they only have their own share. And let's see just the process from the perspective of one node, of the ith node. So pi will compute those two special values, e and f. And those are simply, he takes his own share of x and he subtracts from it his own share of the beaver triple, r. And then the same for this value f, except he subtracts from his share of y the other half of the beaver triple, the other element. Then all the nodes exchange this information. So each of them, they exchange this EI and FI, so that every node has the EI and FI of all of the others. And then they can now perform this summation of all of those EIs and FIs to come up with the actual non-shared value, E and F. And the crucial part is that this E and F, they don't leak anything about the secrets X and F, because R and S are random. So if you have a value that is fixed, not random, and if you subtract from it a random value, then you get a random result. So it doesn't leak anything about what the secret is. So the fact that they exchange their shares and they sum them doesn't make them learn anything new about X and Y. But they have those values, and they're instrumental in what happens next. So next, every node in isolation will perform this magic computation. So he will take his own share of the beaver triple, T, then multiply the E that he computed by his own share of the beaver triple, then add to it F that he recovered by his own share of the R, plus E and F that he recovered, times this 1 over m. Now, this 1 over m looks a bit weird here, so it doesn't mean, it will work if you have an inverse of m in the field, but in principle, that's not so critical. You can also make one node to hold the whole value EF, and all the other nodes just to hold 0. The idea is that when you sum all of their shares of E and F, they end up with E and F, but E times F. But for the moment, just think of it like EF divided by m. And the claim is that whatever each node computed as Zi is actually his share of the result after the multiplication. So that's the claim. And Why? We see here, essentially we want to show that when you summed all the shares, as we computed them in the previous slides, we will get x times y. So first we rewrite x times y in this way, which is exactly like the way we set E and F, right? Like E was x minus R and F was x minus S. So x times y is this multiplication. When you expand it, you end up with this. And now when we are summing the shares, we want to end up with this value here. So summing the shares, simply if you go back to the expression of Z, we had TFI. So now we are summing all the TIs, and we end up with R times S, because by definition T equals R times S, if you remember from the Beaver triple, right? Then we have E times, you're summing all of the S's, you end up with S, F, all of the R's, you end up with R. And now this is where this 1 over M comes into, because you sum all EF over M times, so M cancels and you are left with EF. And if you just like sum this part, you end up with exactly what we expected. So that's why these Beaver triples are helpful and work. And it gives you a bit of a roundabout way to compute multiplication using linear operations with some extra communication. So now, equipped with this new tool of Beaver triples, and keeping in mind that addition and multiplication by public constant is linear in the shares, meaning each node can compute this independently without any additional communication, and having a way to compute multiplication on shares using Beaver triples, now we can actually apply some check on this original function that we had. Now, the problem was we don't want to reveal A, B, and W. So now every Pj, every node will hold shares of those three, A, B, W. And on top, they will also hold shares of Beaver triples for every multiplication present in your polynomial. And in this case, we have two multiplications, so AW and BW. So for each of those, in an offline phase, even before the protocol starts, we need to make sure to distribute the right number of Beaver triples to each of the nodes. So that's what we do here. And I think the first step is it already illustrates how the MPC computation works, because the next steps are mostly linear. So in the setup, we want the nodes to collaboratively compute this value, the claimed value T prime, without knowing A, W, and B, but only having shares. Well, each node simply starts by computing A times W, just following the Beaver triple multiplication. So I won't go in detail here, but that's exactly what we described in the previous slide. And the same for BW. So as a result, they end up with their shares of AW and BW. So they now have shares for this multiplication without having learned anything about A and B and W. So now every Pj, like every node, has computed its own share of T, and if you sum them up, you end up with the final value. And in the next steps, I mean, we just follow Sumcheck, except we work on shares. And there is nothing much interesting happening here, in the sense that we don't have any more multiplication. So no more communication between the nodes is necessary. For round one, it's just local operations. So the node already has this AW share and BW share, and he just needs to, perform the summation over x1 and come up with his share of P1j. And similarly for P2j, and then the final check. The trick is that once every node computes his shared polynomial, he also needs to send it to everyone else so that they can recombine them. So I have also short animation describing this process in the general case, not for this example, but maybe if you want to ask something at this stage. I hope you can still follow at least a bit. Okay, good, thanks. Not to underestimate your intelligence, it's just that time is very limited and there is a lot of content to present, and I'm speaking very fast. That's why I'm constantly asking Otherwise, given the time, I'm sure you'll get to grips. Let's see with the animation, maybe if something was left unclear. So basically repeating the previous process, but in the general case, not constraining ourselves to a fixed polynomial. So we have the prover that distributes the shares of W and the necessary number of beaver triples to all the nodes, and then claiming his sum is T prime equals to T. So then each node computes its own share of T prime, its own share of T, like Ti, as we saw before. Then they exchange them, sum everything, and come up with the final value. Then this final value goes, I mean, here is depicted that it's sent to all the nodes, but actually each node has already computed it. And then each of them just computes their own part of the PI polynomial. They reconstruct the final polynomial. Then they, like this shows the non-interactive version in which the challenge R is computed as the hash of everything that was seen before. So each node will actually compute the same challenge R, which is important because like the verifier doesn't know whether we work with an MPC setting or like a single prover. So he needs to have the same challenge. And that's the final check where they compute their own like partial evaluation of the function, the share of the final check, and performing they reconstruct the evaluation of the function in the end and show the final proof. A few words about complexity and security and stressing why there are so many imperfections in this scheme so far. So complexity is still 2 to the n for every node, because every node, regardless that he works on shares, he still needs to do these 2 to the n sums. Communication, now we have an overhead per round, because now each node has to send his PI polynomial to the other nodes. So, and the PI polynomials are at most d plus 1 coefficients, and you have m nodes, so m times d. So this is one level of communication overhead. Another level is every time you have a multiplication, you need to do this distribution of beaver shares, like not distribution of beaver shares, but like exchanging the partial information of this E and F computation. So which means that MPC is very sensitive to multiplication. So if you have a polynomial or a circuit that has a lot of multiplications, then MPC will be a problem for you, because then your communication cost will increase dramatically. So much for complexity and for security. Like there are many problems here. First of all, the fact that the nodes reconstruct those partial polynomials, this actually leaks information. They will learn A times W and B times W. So they do not learn A, B, and W explicitly, but they learn the multiplication of those two, and they can potentially do some, extract some value from this. And even worse, the final evaluation, so each of the nodes learns the final evaluation of this, of the polynomial at a certain fixed value. Now this already gives you one linear equation in A, B, and W. So if you can generate more equations like this, you can potentially also recover the coefficients or the witness. Finally, we also work under the semi-honest MPC party assumption, which means that we don't we assume all the nodes follow the protocol. They won't do anything malicious in the sense of, you know, sending invalid shares, sending, you know, or not, or withholding a share. We assume they follow strictly the protocol, but they can still like extract information from their transcript, which is still it's a limitation. And that's where all of the other, you know, parts of our stack come into place. So what we show so far, hopefully gave you a better idea of how MPC works like in detail, but leaves a lot of like empty areas. For example, we don't have ZK at the moment for the reasons that I just mentioned. It's not even an argument of knowledge, it's just proof of correctness. We don't have an arithmetization, so you may think like how this like super contrived problem of computing Boolean sums relates to arbitrary computation. And that's solvable, but we didn't describe it. So that's where all of the other blocks come into play to address those limitations. I will very quickly just show you that in fact it's easy to, like relatively easy to just take an arbitrary circuit, an arbitrary like computation of addition and multiplication gates, and by assigning every gate like to an index, you essentially end up with, you see, like a function that, given some like Boolean values, it will give you the values of the nodes in your circuit. And then you can have a constraint function that is constructed in such a way that when you sum this f over the Booleans a, b, and c, if the result is 0, this will imply that these ABC values are valid assignments of your circuit. And that's where the connection comes between arbitrary computation and Sumcheck. You can actually craft such a constraint function that when you sum it over all the like Boolean possibilities, if you end up with 0 result, you know that your circuit is constrained. I think it's time to already end. So hopefully I gave you a bit of more understanding now how multi-party computation works in order to compute ZK SNARKs. We started from the ground up with little assumptions on the background and like mathematical concept. And on the way, we kind of built a toy ZK SNARK from the ground up, although we only covered part of it, which is like of independent interest. I think if you want to learn SNARKs, it might be one way to get a better understanding. So if we had more time, of course, we could have seen more realistic examples. What happens when you add zero knowledge and commitments and blinding and all the elements that you have in typical SNARKs. So if you are interested, definitely feel free to contact me either on email or my Telegram handle. Happy to chat more about this. Happy to share my slides. There is also a short write-up that accompanies the slides. Happy to share it as well if it will be useful for you. And hopefully by now this picture makes a bit more sense. And we will at least motivate you to learn even more the details of coSNARKs. So thanks so much for your attention. Really appreciate you being here.